end, and then you get ds by
Yeah.
having the differential times dr.
Yes,
the
that's
dr was what I was missing.
okay. Perfect. So in order to determine this, we have 8 number, we have pi, we have r because we have to solve, and we have again r and the r have to be determined from c. So c equals 2 pi r, which means this is 84 equals 2 pi r. So r equals 84 over 2 pi. This is our r here. And dc equals 0.5, right? So we have to determine dr. So c from here, we have dc equals 2 pi dr. When I differentiate to find the differential of c, I have 2 pi times r. R prime is 1, but I have to multiply by dr. And that's how I determine dr. So dr equals 2 pi, I'm sorry, it's dc over 2 pi. I'm going to erase this because it's not clear. So I have dc equals 2 pi times dr, and I'm solving for dr. I need it in the equation, so I can put it in. So dr, I still write dr equals dc over 2 pi. And dc is 0.5. So that's how I get this piece. In order to find the approximate error, we're not there yet. We have one more step, just to plug in the numbers. So first we are asked again to find the approximate error in the surface area. So we determine the differential of S, 8 pi r dr. But now I have to determine these. I don't have the radius. I'm not given the radius. I'm given the circumference. I am not given the error in the radius. I'm given 0.5 for the error in the circumference. So I need to determine these two pieces. Okay, so how do I determine the r? Well, I'm given that the circumference, which is 2 pi r, equals 84 centimeters. So c is 84, 2 pi times r, so I solve for r, 84 over 2 pi. And that's how I get r. But now I also have to get dr. So when I differentiate this now, I get dc equals 2 pi dr. So then dr equals dc over 2 pi. The dc is given to us. It's this tiny error of 0.5, and the denominator is 2 pi. So now we have all pieces, so we can put everything together to find the approximate error. So ds, the approximate error in the surface area created by that error in the circumference. So we have 8 pi. R was 84 over 2, or 42 over pi. And dr is dc, which is 0.5, divided by 2 pi. So I simplify as much as I can. A pi with a pi, a 2 with an 8. And I have 4 times 42, 168. This is 1/2. So this is 2 pi. And I have 64 over pi. And this has to be in centimeters squared because it's the surface area. Now, I don't know if they want the answer to be approximated, but again, it's a measurement unit here. So, I mean, it's not abstract. I should divide. So 64 divided by pi. And I have 20.37. So 20.37 centimeters squared. So what does this mean again? If the circumference is correct, 84 centimeters, there is no problem. But the circumference is 84.5. So it has an error. There is an error in the circumference. That error in the circumference creates an error, an approximate, not exact, an approximate error in the surface area of 20.37 centimeters squared. Any questions on this? Any questions? Okay, part B. What is the relative error? So the relative error is always the error over the exact. Error over exact. Well, ds, we have it, 8 pi. I don't want to put this approximation. I'll show you why. I want to simplify. And the surface is 4 pi r squared. So much easier to simplify. Pi and pi, 4, and I get a 2, and r. So this is twice the relative dr over r. So it's twice the relative error in the radius. And now we can calculate it. 2, I have dr. What was dr? dr was this, 0.5 over 2 pi, and the denominator has an r. And what was r? 84 over 2 pi. Flip. 2 pi over 84 because it's in the denominator. So I'll simplify. You can put in this number if you want, but I'd rather not. I'd rather see what is going on here. So this is 42, and it's 1 over 160 times 2, 84. 1 over 80. I have 1/2. 84, yes. So 1 over 84. Yes, I can approximate that. 1 divided by 84, 0.0119. So this is the relative error. This over this. You have to get the same answer. And the percent will be 1.19%. No measurement unit, no measurement unit. So what is the percent error? 1.19. So every time the circumference, instead of being 84, is 84.5, this is the relative error in the surface, in the calculation of the surface area. 1.19%, or 0.00119, or 1.19%. Any questions? Okay, so we can do this as a review tomorrow. I just would like to finish this. So we can also look at the maximum error in calculated volume. Same thing, but instead of using S, we're going to use volume, V. Okay, last topic here is that linear approximation. Okay, the linear approximation says this. Here's our function. Here's our best friend point P. Of course, this is the tangent line. Tangent at P. So the linear approximation says the following, that near P, not here or here, near P, I can use the equation of the tangent line to approximate the function. That's the linear approximation. So as you know, the slope of this line is f prime of x. So if this P is a, comma, f of a, then the equation of the tangent line is y minus f of a equals the slope, which is f prime, x minus a. We use this at least once every class in chapter 3. We had the point a comma b, or a comma f of a. We determined the derivative. We plugged in a. We determined We determine the slope, f prime of a. So this will be exactly f prime of a because we have x equals a. We always determine this. This is the linear approximation. I solve for y. L of x is the linear approximation, is this line. So L of x equals f of a plus f prime of a, x minus a. Again, what does this mean? It means that the equation of the tangent line can approximate the function only very, very close to p. If you want to approximate the function here, then you have to determine a new tangent. And you will be able to, close to this point, use the equation of this tangent line at this point to approximate the function. If you want it here, you have to determine a new function because it has to be very, very close to that point. So this is the linear approximation. It's the equation of the tangent line to the graph at that point. And another concept is the linearization. They're the same, which means that f of x is approximately this, which is already what I said. So when we are asked to find the linearization, we have to find the equation of the tangent line. When we're asked to, the linear approximation. When we're asked to find the linearization, so sorry, this is the opposite. The linear approximation is this, and this is the linearization. Sorry. Never rush. I'm trying to get to 3.9. I have to get to 3.9. Okay, linear approximation. I'm going to erase this too. So this is the linear approximation, and this is the linearization, of course. That's why it's the approximation, linear approximation. Okay. So linearization, I have to let it dry, so I'm going to write it underneath here, linearization. So this is the linearization, and this is, of course, the squiggling symbol, the linear approximation. They mean the same thing. This one says that you can approximate the function near a with this, and this one says what is the function that approximates the function? What is the linear function that approximates the original function? This. Okay, let's choose an example so we can illustrate. Anything you want from the very beginning. Find the linearization, and then find the linear approximation. Same thing. So let's choose a function from 1 through 4. Anything you want. To find the linearization, which is the function, L of x. Okay, I will choose, which one?
2.
2. That's exactly what I was going to choose. Very good. F of x equals e to 3x, and a is given to us to be 0. So we're asked to find the linearization. We are going to copy this immediately, f of a plus f prime of a and x minus a. All we have to do is fill it in. That's it. So this is 0. So this piece is just x. F of a, I have to plug in 0. So this is f of 0. Can anyone tell us f of 0, how much?
Is it 1?
Perfect. Can anyone find for us f prime and then plug in 0? F prime of x.
Isn't it just 1 again?
F prime. F prime. First, we have to find f prime and then plug in 0. We cannot plug in if we don't have f prime first.
Just e to the 3x.
Careful, it's e to a function. E to a function prime is,
Oh, is it the 3x?
yes, awesome.
Yeah,
3,
my bad.
yes, perfect. And now f prime of 0. Yes, now we can find f prime of 0. What is it?
Three.
That's it. So this is 3, this is 1, and this is x. We're done. So L of x is 1 plus 3 times x. And x minus 0 is x. This is it. What does this say? It says only near 0. Nowhere else. Only near 0. If you want to determine, for example, L of 0.1, it's easier to determine this because L of 0.1 will be 1.3. But if you plug in 0.1 here, you will not be able to determine 1.3, because this is an impossible calculation for us. E to 0.3, I have no idea what that is. So it says, again, that only near 0. If you want to approximate this function, then you should be using the linear function. It's the equation of the tangent line to the graph of this function at 0. Simple as that. That's the formula. That's the equation of the tangent line. All you have to do is just plug in each piece, and it's done. Any questions? Okay, so let's at least start this 3.9. This is the last section, I promise, from chapter 3. And this is more applications. However, there are specific types of applications here called related rates. What is this? What am I talking about? Okay, here's an explanation. Let's say, imagine we have a balloon with no air. Imagine now that I blow some air in it, and then it becomes this, and then it becomes this. What happens in time? Okay, the volume changed. The radius changed. The surface changed. The surface area. So from, let's say, this radius to this radius to this radius and to this radius. So smaller, bigger, 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 bigger. The volume of the air inside the balloon changed. The surface changed. All these just became, by the simple action of blowing air into the balloon, these three functions, these three elements became functions of time. All of them. The volume, the surface, the radius are now functions of time because they're changing with time. Time is the independent variable. The volume increased with time. The surface area increased and the radius increased. But now, all these new functions have derivatives, but that's the rate, right? Have derivatives that are related. They are in an equation. Here's how. Here's an example of just what we just looked at. So I know that the formula for the sphere, let's say this is a sphere, 4/3 pi r cubed. When I differentiate both sides, knowing that this, I'm going to put always a dot under functions of time, so you don't treat this as a variable. But because the volume is a function of time and the radius is a function of time, when I differentiate both sides, I have dv over dt equals 4 pi r squared times the inner function prime. So the two functions, in this case, volume and radius, were related by this equation. But now their derivatives are related by another equation. So that's what we mean by related rates. There are derivatives that are found in a relationship, in an equation, related rates. These two functions are related by this equation. These two, their derivatives are related by this equation. The equations are not the same. This is one equation that relates this function of time to this function of time, and this is another equation that relates the derivative of this function to the derivative of this function. So it's